Hey guys, welcome back to this video on rapid paper review. 2025 started with a bang. There are plenty of interesting papers that came out. I have to do another video quickly because there are more papers that I want to talk about. But first, I wanted to talk about two interesting papers, Deepseekv3 technical report, and also this paper by Meta, which is memory layers at scale. So let's talk about Deepseekv3, which has been taking the world um, with a storm. It is an interesting model. It's open source, as far as I know, and it's doing very well. B, it is very fast, so that means low latency, and C, that it required pretty less budget to train. So those are the factors that are going for it. Okay, so let's quickly jump into the Deepseekv3. So what's new in this model? So first of all, this is 671 billion parameters. So of course, this model is going to be good because it has a lot of knowledge. And then it's an MOE architecture in which only 37B are active at any given moment. Now, the secret sauce that makes this model tick, which is what I'll just quickly review. Again, if you want to learn more, just read the paper or watch another YouTube video which just focuses on this video. The focus of this series is to just quickly give you an overview of what are the interesting papers out there. So a couple of things. What they do is they have this latent attention, MLA kind of thing, where as soon as your token comes in, a latent representation is generated for that, or for your input sequence. For each of them, a latent representation is generated, and then so this is a smaller dimension representation, which is then upcasted into query, keys, and value matrices. So you have two latent representations, one for a query and one for key and value. And from those, you generate keys and values. So it's just a way of compressing the QKV things. And what it does is it, with very little effect on performance, it increases your output, or rather inference latency, or reduces your inference latency, because now you have to store less things in your KV cache. So that's what it does. It's not so much as improving the model, but it's just something that improves inference. But in the MOE, what they have is, so in MOE, you have a router which selects top N experts. Here they have a few experts that are always triggered, and then a few for which we do top N. So they have this combination where some experts always trigger for tokens, and some, for some you do the standard MOE, and then you combine the results. That's one of the key differences. And then they do some kind of like a load balancing by adding a bias term. I don't know. I mean, it just worked for them, but there's nothing really sciencey about this. Basically, they keep monitoring how the loads are being distributed to different experts, and they manually tweak the bias to distribute the balance equally. Yeah, there's nothing. A lot of interesting things there. Then instead of just doing the next token loss, what they do is they do multi-token prediction. So they not only do the next token, they'll do the next to next to next token predictions. And so they basically take the output representation, and then they do another transformer block on the next token, and then on the next token to compute like 2-3 tokens ahead, and they compute the loss, and then they back propagate it. So during inference, so these are additional structures on the transformer which are there during training time, but during test time they're removed because you only care about the next token. So during training they do multi-token prediction, during test they only do the next token. And this has been there was this paper Eagle by, I guess, Microsoft or Meta that did this. So you can read that paper, but this is another thing that they do. Other than this, let's see. Then they have this whole training framework where they do FP8 training. They had to do, because of, I guess, the hardware restrictions. They use H800 hardware instead of like H100 or H200s, which have less memory bandwidth. So they have to, so for them, like the most efficient way to do is do computation in FP8, and they have some strategies of like computing, um, doing matrix multiplication in FP8, and accumulation is in FP32 or FP16, or rather FP32, and then the same standard FP16 or BF16 stuff. But basically, the innovation here is they do, because of the hardware restrictions, they do training in FP8, which turns out well for them. That, I think, is all this stuff. And because of all of this, their data mixtures, the model turns out to be performing really well. So so yeah, so here they show all the different results, and the board ones are where it's outperforming, and it seems to be doing pretty good. But then, yep. So I think that's pretty much it. I wanted to talk about this paper. But again, this model is actually doing really well in the real world. So you might want to, if you're using ChatGPT, or GPT-4, you might want to try this one out, especially because it's extremely cheap to use. The other paper is memory layers at scale. So, okay, so where are associations, quote unquote, memory stored in transformers? It's primarily the MLP layers, right? So you have your attention, and after that there are some feed-forward layers, and those are the feed-forward layers are where a lot of associations are stored. One way to increase that is this MOE, where you not only have like one feed forward, now you have like a bunch of feed forward layers, and you select a few. So this is scaling the MOE setting, but in a slightly different way. So the way MOE scales is, you can think of it as extending horizontally, where you have a lot of fully connected layers, and you pick two. Here, their idea is that instead of scaling horizontally, we will just scale vertically. We will make our fully connected layer extremely big and make it efficient and so on. And that's how they do. So their idea is roughly the same. So just like in the MOE setting, when a query comes, when a query comes in, when I say query, this is an input token, post attention, right? So values have been aggregated. So this is post attention. And they do some kind of somewhat like an attention mechanism here. This is not your standard attention. This is post attention. So your input comes in, which is n-dimensional. They have a set of keys, and they have a set of values. Now, what they do is they select the top k indices by multiplying key to your query, and then they compute the softmax indexed on those indices, and then they combine them with the values. Now, this is very reminiscent of even the MLP layers, right? So your MLP layers are, so you have an MLP layer, then you have silo, and then you have another MLP, right? So let me actually pull up the equation first. Yeah, so in the diagram, if you ignore this block, so this part is the standard MLP layer. So you have a weight matrix, you have the silo activation, and then you have the other one. So basically, it kind of looks like this. So you have silo. So forget this Y thing. You have silo acting on X transpose W1, and then you multiply that W2, where silo is just X times sigmoid, and so on. So let me just quickly go into details. Here I have ChatGPT. So silo is just input, element-wise product of sigmoid of the input. And the whole looks like, so first you have an up projection. So this is the silo thing. Let's go back. So you have an up projection, apply silo, and then down projection. So if you rewrite that, this kind of looks like this. You can do, so what am I trying to say? So if you forget this y factor, so this times this means there's a sum happening because it's a multiplication. There is a sum over n dimensions. So instead of if you do the sum over the top two, this starts resembling indexing. So right now, when you multiply, you index over, you take all the columns of W. But if you just do top n, you will just take top two columns, and that's what this is resembling. So just some parallels. So essentially, we take the query, multiply it by key, find the top n indices, get the softmax, and then take those items from the value matrix. And now you can imagine you can make K and V to be extremely large. And that is where you store your memory. So this is what I meant, that we are expanding vertically. We just have one MLP layer, and in this, just this, and we just expand, like make the matrices extremely large. And now when you have like large matrices, like doing this kind of computation is hard, and they do it by this product key lookup. This is an efficient way of like breaking the complexity down from O(n) squared to O(n), or from O(n) to O square root n. So just splitting it into two vectors and doing the search. Not super important. This is a commonly used trick. And then some GPU embedding searches, like some GPU optimizations, like how they shard the different, how they shard the matrices in two different ways, and so on, like across two different GPUs and so on. So this is how the model looks like. So they zoom out. So on the left side is their module. So you have your standard attention. When the attention comes out, regular norm, and then they do you multiply it by the so when they say sub key 1, sub key 2 is splitting the key into two, this fancy search by splitting the key matrix into two parts, and then doing the two parts separately and then combining them. Then they find top K, do the softmax, find the values. That is it. So you replace the standard MLP with this. They found that this doesn't work very well in practice, so you really have to put back this silo thing and you do an element-wise combination here. But for this, it seems to work. So I'm not too impressed by what they've done. It's just another way of scaling memory, or rather rote memory. Either you do like this MOE, expand it like this, or you just do it in one giant matrix. But and they only show results in like two things: natural questions and trivia QA. So I wonder like how really effective this is. But interesting nonetheless. So that's all for this session. I'll see you guys next time.